Thank you so much for what a warm welcome. I can't tell you how excited I am to be able to talk to you today a little bit about what our front line is, and in a way, what some of the front line of New York City is dealing with. Um, and also thanks to so many of you who've decided to take an hour or so out of your day to hear about some of that. So um, a little bit about the firm briefly, right? We're at Enter Engineering Associates. We're right in the heart of Midtown Manhattan. We are an MEP engineering firm first, so we do mechanical, electrical, plumbing, fire protection, low voltage systems, and the like. We do some civil stuff. But a close second for us is sustainable service. We've been doing this since 1960. Um, we do projects of all kind of shape, flavor, typology, generally larger stuff than smaller stuff, half city blocks, full city blocks, the type of scale that's kind of on the screen. We do single family, smaller infill jobs and all sorts of other stuff of different types, but we really thrive at the intersection of MEP and sustainability. The project that's on the screen is one of the NYSERDA Buildings of Excellence Awards that we've been fortunate enough to claim. It is a Variety of Boys and Girls Club project in Queens. And so just to give you a little more flavor of what we do, there's a lot going on at this project to be excited about. There are geothermal systems. We're rejuvenating and rebuilding a 100,000 square foot Boys and Girls Club and putting a couple hundred supportive, affordable dwelling units on top. The project sponsor is amazing. He's actually the chair of uh, the club executive committee, and is a former city councilman who actually helped pass Local Law 97, which is our city's carbon tax, basically cap and tax kind of policy for buildings. He uses this building as a nexus for educating the community and beyond about sustainable design practices, both for buildings and beyond. And we're really leveraging that through the project's design. We're making a museum style moment in the lobby. We're gonna have live kiosks where you can literally open to the public, look at screens and interact. What's the solar system on the roof producing? How much energy is the geothermal system using, and so on. And so we're not afraid to push. And some of the stuff we're going to talk about today on a different project is hopefully kind of representative of that type of thing. To give you a little bit more look at where we're headed, we really like the concept of sustainable circularity, which maybe a lot of MEP engineers don't really talk about. So I want to spend a few minutes kind of trying to ground in what that is and how we can bring that to the sustainable concepts of all facets of building design. But in particular, we're going to take a deep dive on how we can do that for MEP system selection, the heating, cooling, ventilation, domestic hot water systems, and stuff like that. So what is circularity, right? The traditional economy is a historically make, take, use, dump. The classic examples of this are single-use plastic bags that unfortunately end up in landfills, single-use plastic bottles that can unfortunately end up in the ocean, right? Where circularity asks us to make, use, reuse, transform, recycle, and really in its loftiest way, to live as though we aren't here. So in my sphere, we see regulators starting to look and nod in this direction. In the city, the DEP, who's responsible for our cities and our sewers and our water mains, rather, passed a set of rules in 2022 that basically said, hey, development isn't exactly a right per se. If you're going to build a new building or substantially renovate a building, from a stormwater management perspective, try and behave as though you were a grass field. And so there's design practice and calculations and a review process that is really trying to push us to capture stormwater, reuse stormwater, infiltrate stormwater, and really live as though we aren't here. So it's kind of a wonderful example of one of our local regulators kind of starting to grab one of these concepts of circularity. So that is, of course, something that's happening at a building level for us. And what I want to spend a little more time talking about is how we can channel that spirit and do more at a building level. We can reduce and we can reuse. It can literally be materially based. The project we're going to talk about is using recycled brick in the facade. So that is quite like the plastic bag example, single-use plastic bag example. But if we dig deeper and push more, we can bring these types of concepts to MEP system design as well. So just to plant a seed, right? We're moving buildings to electrification and using heat pumps, and that's good so that we can become carbon neutral ready and the grid can catch up with us. But let's think about what a heat pump actually is. When we burn fossil fuel, we are using something, we extract heat and it's gone. That is quite literally linear. Whereas with a heat pump, when I'm heating my office, if it's an air source heat pump, I'm literally just moving heat in and out. And so nothing is created or destroyed. If I heat my office with a heat pump, an air source heat pump, and then I open the window, everything can achieve equilibrium again within a couple of minutes, and we haven't actually used something. And so I want to keep that in our mind as we start to talk about systems and heat pumps and how we can actually become more circular in our design and practice. So the project we're going to spotlight is a wonderful project. It's the Malcolm Shabazz Harlem Plaza. It's on 116th Street in Harlem, and its origins kind of come in two places. One, there is this open air market that serves the neighborhood. It spotlights West African culture. It's through lot now, and they do wonderful things, but it's open air. And so one of the drivers is to make this market, to uplift this market, to enclose it, to provide cooking, restaurant style opportunities. There's commercial kitchen, commercial refrigeration that's going to happen. There's flex spaces and all sorts of other stuff that we have to address in the design. And then the neighborhood also badly needs affordable housing. So the 2 9-story towers that rise on either street face will contain a total of 100 affordable dwelling units. This is also a NYSERDA Building of Excellence hopeful, so we're waiting for this next round to close, and we'll see how we fare. And we have a wonderful team in Think Architecture and Design, and we're also in direct support of the mosque, which is the direct descendant of Malcolm X and his grandson, and also proceeded construction. So, but let's start to get into some of the details. I started saying that we live and thrive at the intersection between MEP and sustainability. And we do. In a way, we've kind of gotten so used to it that what we want in its root nature is already in our mind. We know we want to electrify this building, and we know we really want to try and take this to passive house. And so we have that mindset, and we have the support of the design team to that end. So if we take that for granted for a second, the next conversation really becomes, what is the heating, cooling, ventilation system that we want to use to fit this project and this project typology? So in our world, there's kind of a classic debate that's happening that's kind of evolved and developed for residential typologies. On the left, we have split variable refrigerant flow systems. We'll call this VRF as we move through the rest of the talk. And packaged terminal heat pumps, we'll call them PTACs or PTHPs as we move through the rest of the talk. Both all electric, both air source heat pump, using refrigerant to drive a heat pump cycle. But the key difference you can read really in the first word of each: split and packaged, right? So the split VRF system takes the two parts that heat and cool. I'll keep picking on my office, the fan that I experience directly that heats and cools me, and the condensing unit with the compressor in it, and puts it on a roof or some sort of outdoor remote location, which is really doing the work of the heat pump refrigerating cycle. And so there are benefits traditionally associated with the system. They run at a little higher efficiency. The noise of the condensing unit gets put outside. We get a little bit different perhaps better, more aesthetic product because the indoor fan units have a little more variety and optionality. And also there's no facade punch, which we see obviously in one of the pictures for the PTAC or the PTHP. The difference is, of course, as we package the system, we basically put the two parts of the split together. And so the fan is just on the inside of the wall, and the condensing compressor unit that's driving the cycle is just on the outside of the wall, and we land with a facade punch. So let's go a little deeper though. And let me orient you to some of the major pros and cons between these two types of systems, VRF on the left, packaged terminal heat pumps on the right. The green is to represent the pros, where let's say PTAC is winning, so to speak, and VRF is winning, so to speak. And the further you get from the center, the larger the perceived benefit is. So let's start there for a second. For the PTAC on the right, there's kind of two prime benefits that a development like this would seek to gain. First, without all of this refrigerant piping, the PTAC system is quite a bit cheaper, and it depends on the size and flavor of the building, but here it's running about 1.5 to 2 times cheaper than the VRF system. The parentheticals that we include on the slide are actual numbers for our project, so if you want those for point of reference, they're there. But the second major benefit that comes with PTACs is also more on the operational side. The way these things are metered and electrically wired for affordable housing projects, it is much easier and cleaner for the owner to pay for heating and the tenant to pay for cooling, which is in line with traditional utility allowance structures. VRF struggles here because if I go back to the prior slide for a second, for larger scale buildings like we do, the only cost-effective way to deploy VRF is with common condensing units. So these condensing units on the roof are shared, and we typically would vertically stack, there's 5-10 apartments or something in a vertical apartment line on one condensing unit. There's a lot less refrigerant in the system. There's a lot less piping in the system. There's many fewer condensing units, and it's really the only practical way to do VRF in a large scale multifamily project like this. So to make that work, the metering, the flip side of what I was just saying for PTACs, the metering gets more complex, and the owner basically electrically pays for the heating and cooling use of the system and has to go try and collect cooling use from the affordable tenants, which is a difficult kind of financial proposition and can result in some amount of loss run on the operating cost side. So to boil all that out, the two main benefits that come with the PTAC style system are basically lower hard cost and the prospect of lower operating cost in that metering gambit that I just described. And not surprisingly, developments are interested in lower first cost because sure, if we have lower first cost and lower operating cost, we can do more with less. So that's obviously a grounded idea. On the flip side, right, the main thing with VRF is that there is no facade punch. And this is really the only traditional way that we can make this building get through Passive House protocol. So that sets up the wonderful confrontation that we're trying to head off. Can we get PTACs through Passive House? We're going to talk about that for a whole bunch of time here. But I want to focus on what might traditionally get lost, which is these other two green items in the middle, which are talking about embodied carbon in materials and embodied global warming potential within the refrigerant circuit itself. So you see we have 2 to 3 miles of refrigerant piping saved with the PTHP system. Let's hit the pause button on that for a second because I really want to drive this point home. I don't know, I get my exercise trying to run. So I think of this as a 5K, and 5K is 3.1 miles or something. So, you run it 20, 25, 30 minutes, whatever you run a 5K, and that's a lot of refrigerant piping to be chasing you around. And so when you think, well, okay, well, what is that in terms of global warming pounds of potential? Well, it's 2 million pounds of global warming pounds of potential. What is that? That's not really a relatable number. The way that we traditionally talk about global warming potential is in the amount of carbon dioxide equivalent that would be emitted. So if we released all of the refrigerant in this, call it 3-mile network of piping, it would be the equivalent of releasing over 850 metric tons of carbon dioxide. That's kind of a big number, but let's continue to put that in context. That's the equivalent of taking the average of 186 cars off of the road. But in terms of operational carbon, the way our city is dealing with carbon footprints and mitigating them, that is equivalent to the 1.5 to 2 times the entire operating carbon footprint of this building in sum. So let's really hold that in context as we think about why we want to push for packaged systems. Are we entitled in this linear way, this linear economy, are we entitled to deploy that much refrigerant on a job? Or is it more circular in nature, let's say, to try and pursue this more package style system? I have to give a nod to NYSERDA here for a second. For those who pay any attention to the Buildings of Excellence competition in New York State, between the last round and this round, they actually changed the criteria to, I don't want to say reward, but try to reward or benefit projects that find a way to use more packaged systems, because NYSERDA understands this and the significance of this. That's also not to say that we're going to release all of this refrigerant. This is if we turned over all of the refrigerant in the system, but all it takes is a nail in the wrong place to do a lot of harm, right? And that's really kind of the point. All right, so therein lies kind of the reasons why we want to take on this challenge of bringing packaged heat pumps to Passive House. So, but that makes this kind of grand confrontation, because what is a packaged heat pump? It makes holes in the facade. And Passive asks us to have a very tight facade that is very highly thermally performing, that mitigates thermal bridges. This thing is basically running counter to all of that. So we're going to talk about how we're mitigating that on this project and other projects. But before we do that, let's talk a little bit about which PTHP. There's two PTHPs, two styles of PTHPs that are on the market now. One, you may have seen this, more historically, you see these 42 by 16-inch facade punches on the facade like we saw in the first graphic, right? So there's the traditional model that fits that sleeve. And then there is what I'm calling a more modern style. It's coming largely out of Italy, and due credit there. They're being sourced out of a couple of factories in Italy, where they found a way to basically take all of the process air that the heat pump needs through 2 8-inch rounds. So again, to the green, green is the pros, again, one versus the other, and at the more extreme, what we've found more significant for us at this given project, right? The more modern style offers a much smaller facade penetration. And the other thing is this product line and typology also offers the potential to incorporate packaged energy recovery ventilators within the unit, so we can have local balanced ventilation as opposed to a centrally ducted system on the roof or something like that. On the flip side, in our experience, and I'm not advocating for one of these PTACs one way or the other, we are deploying both on a number of projects for different reasons. The traditional PTAC wins the argument on the bottom left because it does run almost half the price. That's, again, we're coming back to cost. That is a significant driver for any development. And we have found, we're specifying these products and feel a responsibility to doing that as best we can. We've done a lot of due diligence on these products, and we found in general terms that the traditional PTHP manufacturers have done a better job torture testing these things. The domestic supply chain is a little bit more proven. The developers and the contractors are finding a little bit more comfort there. So for this project, we're actually deploying the 42 by 16 inch, the traditional PTHP. For whatever reason, I'm not advocating for either one per se. From our perspective, bring it on. If we can prove that a 42 by 16 PTHP can work on a passive job, we can certainly prove that both of these things can win the day. So we're not ones to shy away from a challenge. So let's go. We'll take this in two parts, right? We got to talk about air tightness and then the envelope thermal performative side. So we'll do air tightness first. We're pursuing PHI certification, not FIAS. And so PHI had a kind of a standing waiver that just expired at the end of the year for projects that started before December, that if you're going to try and do this, and this is obviously another organization giving a nod towards the package concept, in any case, they'll relax the building air tightness criteria from 0.6 to 0.8 ACH 50. Well, in the yellow section of this slide, we basically can quantify what that means in terms of additional CFM we are allowed through the building at blower door test time. And it works out, as you crunch the numbers, to effectively 4,500 CFM more leakage through the facade. And as you break that down on a PTAC level, it's 18 CFM a PTAC. We've done a lot of work with a number of manufacturers in this space. I'm not at liberty to actually disclose test results because it's on the front line of the manufacturer's competitive advantage. But we have seen unimproved, let's say uninitiated PTACs bench test to basically 20 CFM of PTHP. And there's been a lot of movement to address this exact concern. And we've seen test results trending towards 3.5 CFM of PTAC. There's labyrinth sealing, there's mechanical gasketing happening. There's a number of things that different manufacturers are working towards. But the short takeaway from this slide is with actual test data, we feel with high confidence that this will work. Obviously, the proof will be in the pudding when we actually build this thing, but there is a substantial margin between a 3.5 CFM per PTAC on a bench test and 18 CFM allowable at testing time. So we have very high confidence that this will work. Let's talk a little bit about the envelope and the thermal bridging aspect of this. I'll start by talking about how New York State and New York City Energy Code addresses the packaged unit. And this is just a straight excerpt from the code. The code says, if the total area of penetrations from through-wall equipment is more than 1% of the opaque facade, when you do a comm check, when you do a res check, when you do a code energy compliance with the building department, thou shalt take that as a U factor of 0.5 or an R value of 2. Right, the traditional code assemblies, R18, R20, or when you push to R30 type of walls with a passive type of a design. So that's quite a hefty penalty to saddle yourself with. So first, this traditional 42 by 16 inch sleeve, which is over 4.5 square feet, and you picture a 10 by 10 wall in a residential bedroom or something, right? 4.5 is 4.5% of 100. So we're well over this threshold. Our projects have been historically taking this penalty, whether they're going passive house or not. Again, I wish I could tell you a little bit more about what the manufacturers are doing, because we are kind of trying to advise them and pull them towards what we want the market to do, thermally break the assembly this way, add insulative inserts here, and so on and so forth. The short is manufacturers are working to give us a listed, tested product with an integrated R value beyond just this 2 code value, 4 to 6 to 8, plus there's some that think they can do more than 8. The question we've kind of asked and are working through with them at a longer term kind of scale is, will these products gain formal passive house certification so it's much easier to integrate with passive house design? And we're doing what we can to facilitate that. In the interim, right, we're doing heat remodeling, thermal bridge modeling, whatever software you like. And the psi value, the chi value, it works. It works. Right? But there's a number of things that the manufacturers are doing. So let's jump for a second to domestic hot water systems now that we've kind of pushed through HVAC a bit. I like the way this slide frames the conversation, right? Passive house is amazing. This, we know it places great focus on energy demand at large, on the envelope, and heating and cooling demand and so on. And not to say that domestic hot water gets lost in the sauce per se. It doesn't, because it's part of energy demand, but it becomes all the more important when we make a passive house project. And I like this graphic that comes out of a study from Britain that shows on the right, this is single family homes, but it makes the point. On the right, the average non-passive house, call it a quarter or 23% of the energy consumption is supporting domestic hot water production. Whereas once you move to a passive house, the gray semicircle is basically, call it 53% savings that this study shows, but hot water becomes all of a sudden half of the energy consumption pizza pie. So let's turn our attention to that in as circular a manner as possible. What do we do about this? I'm going to use it again, invoke circularity. It's almost like the Superman on the chest. Not that it's the only word that we need, but we love this concept, right? We spoke at the beginning about trying to move from combustion, which is something that's linear and used, to heat pumps. And a lot of industry, locally, nationally, and globally is moving in that direction if it hasn't moved in that direction in the first place. But there is something huge for domestic hot water in this concept that we're going to talk about for this project. When you move to the ability to move heat, it can unlock all sorts of heat recovery opportunities for domestic hot water. Before we get there, though, let's talk a little bit about the source, right? So what source am I asking this heat pump to use? Well, air source is one. Right. But the problem with air source is that the coefficient of performance, or the efficiency, is relatively low. What's the COP? COP is the ratio of the energy out versus the energy in. So if we say an air source heat pump has a COP of 2.5, for every kilowatt or watt of electricity I send to this unit, I get 2.5 units out of just moving energy. That's good. 1 for 2.5 is good. Water source, we can push to the low 3s, but with blackwater source, we can push to the high 3s and almost the low 4s. And so this is the product typology. This is the typology that we like to use blackwater source heat pumps for. Let's ask the question though, why the efficiency for blackwater source heat pumps is so much higher than water source and air source? And let's focus on this blackwater box on the bottom left for a second. Heat pumps thrive with a consistent source temperature. We've heard these buzzwords, cold climate air source heat pumps, right? The PTACs of old could not run a heat pump cycle to frigid temperatures because the technology just wasn't there. And so the COP, or the heating efficiency of an air source PTAC, falls. The old ones a lot and the new ones a pretty hefty amount. If you ask an air source PTAC to heat at 80 degrees outside, you might have a COP of 4 because it's got a lot of heat that it can pull out of an 80-degree airstream. If you ask that same PTAC to heat at 0 degrees outside, the COP might be 2 or even sub 2, 1.7, right? So with a blackwater source heat pump in a residential building and other typologies, we can really come closer to achieving circularity. When we feed this, when we take the waste stream, literally the sanitary sewer waste stream off of the apartments, what's coming out of our shower drains, our toilets, our sinks, our washing machines and dishwashers and that type of a thing, sewers run consistently between 50 and 70 degrees. So as long as we're in the building doing our thing, so to speak, the blackwater source exists. And within that, we can unlock a higher operational efficiency. And we put the circle on this graphic because it really, we feel this is an invocation of circularity, but we take this a step further. We love mixed use buildings because within the construct of mixed use typologies, there is always an opportunity for energy recovery. We have markets, we have the market and we have refrigeration racks for the restaurant stalls that are going to exist down there. They need constant cooling. And since heat pumps move energy, they are rejecting heat. Let's use that waste heat and send it to this blackwater source stream. And we are. So not only are we getting a COP in the high threes, we've pushed the operating efficiency of the system over 4 simply by looking around for waste energy that we can use. We all see this. And if I can be so lofty, this is the type of thought process we need to try and channel to make buildings self-sustaining and cities self-sustaining. You stand under your refrigerator with bare feet and in the winter and you feel heat, right? Because the refrigerator is doing the same thing. That's on a much smaller scale, but that heat is being wasted right into your space. Can we reclaim that? Can we reclaim all of the other waste energy around us so that we can move away from a linear use to a more circular use of energy? A couple of words on the global warming potential of this. It is obviously much more dramatic for the HVAC system with 3 miles of piping. These systems are more centralized. But first, the blackwater source heat pumps that I spoke about use an advanced refrigerant. That's the R513A. And the global warming potential of that is roughly 1/3 of R410A. So that's victory number 1. But the other thing, and we're going to look at the spatial design of the market on the next slide, so this will get driven home a little bit better once you can see the imagery. But we are able, through artful design, to do mini split domestic hot water systems for the market. These are not great at large scale buildings. They have very short limitations on the refrigerant piping that they can accommodate, but we found a way to put CO2 mini splits in for the actual domestic hot water production of the market itself. And they use R7, I'm calling them CO2 mini splits because they use R744 as the refrigerant. And CO2, of course, is the reference gas that all of this is based upon. So we've effectively got a 0 or near 0 global warming potential with these mini splits because we're using carbon dioxide as the refrigerant, and they also happen to operate at a very high COP. So that's another way we're kind of winning and trying to invoke circularity in the design. So this kind of makes a segue to the last section of the talk, which is, so now we've pushed through the heating, cooling stuff, the heavy hitting domestic hot water stuff. We're not ones to stop there. We're trying to bring circularity into every other aspect of this project. So let's spotlight that for a couple minutes before we close. This, and I have to give a shout out to Jack Esterson of Think. I love architects that can draw this well. I cannot by any stretch draw like this. I could stare at these drawings. I love them. They make me happy. But this is the setback. I'll go back for a second. This is the setback between the two towers. Where is it? Right? This is the setback between the two towers that lives above the market. And so with a residential use right above and a market right below, we said, how can these two spaces rely on each other in a circular way? So we're deploying skylights above for daylighting and to create a natural barrier in the amenity setback terrace itself to create separation in an architecturally artful way that I cannot take credit for. And there's also this mechanical area where we're recessing the domestic hot water equipment and some of the other stuff that wants to be as local to the market as possible, and also use that as a separation. So that is a little bit of an architectural concession, but it enables us to do things like deploy those R744 domestic hot water heaters, for example. And with a team like this, it's not that hard to get that to happen. So the skylights are daylighting a substantial portion of the market, and it's going to save us 7 megawatt hours a year. So that's certainly not an insignificant contribution to the project. And we're also not afraid to push. By code, we have to mechanically ventilate with forced fans and heating and cooling this market. But we would like to use these skylights in an operable fashion during the shoulder season period at 65 degrees outside Fahrenheit, 68 degrees, where we can bring in fresh air, get free cooling with airside economizer and that type of a thing. This will save us ductwork, dampering, controls. It'll save on operating costs and carbon footprint and all that sort of stuff. But it doesn't exactly reconcile with our building department and the code protocols. We have a process for CCD1s, which is basically a code variance, and we have found leeway with the city building department where we have specifically brought code and energy use to a loggerheads, and we found the city's been pretty sympathetic to this. So we're making an appeal to see if they will let us naturally ventilate this marketplace corridor to save energy, and we're hopeful that we'll succeed, but that's in progress. So just the last couple of points, is just going further. We feel as though any project like this should really be striving to put solar panels on the roof. First of all, with the incentives nested within the Biden administration's Inflation Reduction Act and otherwise, the payback periods on solar arrays have fallen, and in some years can be 1 to 2 to 3 years, which is extremely investable. But also back to the concept of circularity, what are we entitled to do? And I think about this the way our city DEP does, again, that example with the sewer and the water. If right, we struggle with large buildings because our volume to surface area ratio, this roof is not large enough for me to offset 100% of the use. That's the dream. Single family homes can be designed in that way. When you stack 100 apartments on top of each other, you just can't do it. But 18% of the site is certainly valuable because it's 18% of the site. And so we challenge ourselves and our developers to really think about making the roof do this. We've talked about solar facade on other projects, and we're trying to do that too. We didn't stop at daylighting just the market. It's a little harder to do this in residential corridors, but we're daylighting parts of the corridors, so there's an energy savings there. More literally, as we mentioned, we have a recycled brick facade, so we're literally just taking a waste stream and turning it into something usable. And then to reconcile, there is a confrontation, actually, as well-intentioned as our DEP is with all that stormwater management stuff that I've spoken about. It makes an unfortunate confrontation because they want green roof and plantings, and the sustainable side of the world cares about that because sea level rise and stormwater management and significant precipitation events all matter. But at the same time, we're fighting for that solar array on the roof. So the way we've artfully dealt with this, we have this valley of sorts between the two towers that is not really viable for solar because the two towers shade each other. So we're deploying rainwater harvesting in there to effectively serve both masters, if I can say it that way. I like to close kind of with a challenge. I started our sustainability division, about a decade ago, for a number of reasons, right? But one core reason is just to try and leave the earth a better place. And it has really changed the way that we think. We in a way pride ourselves on trying to start a project conversation with sustainable design intent. And so if you can do that and push others to do that, it is one of the challenges of our time to head on. We're not afraid to ask for more. And I would ask you to not be afraid to do the same. Push for whatever opportunities you can. Push the envelope literally. Try and think beyond yourself. We're not afraid to think beyond ourselves and participate where you can, right? There's two examples in this package in this talk where we're literally trying to help lead manufacturers to what we need. Thermally break the PTAC assembly this way so we can get our cake and our cake at the same time, a package system and passive house. And don't be afraid of engaging regulators either, that code variance thing that I was talking about, so that we can naturally ventilate the market. Of course, we need to stay practically grounded, because at the end of the day, we have to make it work. Sometimes the building department says no, we pick up our pieces and we fight another fight somewhere else. But anything you can do to keep pushing, I would applaud you all. I can't thank you enough for giving me a part of your afternoon, and I hope you were able to get some value out of this. Thank you all so very much.
I really want to invite everyone to unmute and give Ed a big round of applause. That was not just some value, Ed. That was an eternity of value, some circular value.
Well done.
Absolutely.
Fantastic.
Thank you, Ed.
Thank you very much. It's much appreciated.
I'm glad you're hopeful for the buildings of excellence, and I'm about to consider you a national treasure.
Ooh, that's
So
a big.
thank you so much. That was really, really fantastic. I'm going to watch this over and over again. I'm sure we're going to have a lot of requests for the slides, so perhaps you can share those if you're willing. We have a lot of great questions in the chat, Ed, so we'll get to those in just a minute, but first we're going to hop over to Zach for a thank you to our sponsors.
Yeah, thank you. So I want to start with our stakeholder partner, NYSERDA. Big thank you to the New York State Energy Research and Development Authority. Thank you to our founding sponsors, 475 High Performance Building Supply, Ingui Architecture, Glavel, Minutair, Partel, Rockwell North America, Stillcorp, and Zola Windows. Thanks to our champion sponsors, Bowizo, Gradient, Icon Windows and Doors, Intelligent Membranes, PH Air Seal, and Source 2050. And thanks to our patron sponsors, Brennan, Euroline Windows, Holstrom System, Inotech Windows and Doors, Lamelux, Longboard, Owens Corning, RDH Building Science, and Sanderson Design. Thank you so much.
Yes, definitely. Thank you to all of our sponsors. Fantastic. We can't do any of this or bring you any of this great programming without them. So please check them out. Also, connect with Ed online. I know Kim is dropping in links in the chat, so you can do just that. And with that, we are going to kick off some of our questions. Up first, we have David Levin. David, would you like to unmute and ask your question? Levin or Levine?
Levine, hold on a second. I have to
Thank
find
you,
the question.
David.
I have
Sorry
to
about that.
find the question.
I can help you with it.
Yeah, what does it say?
Who is the architectural firm you worked with? Was your first question.
Well, that was Ed. Ed, I apologize. You mentioned Think Architecture for the principal presentation. I guess my question was the initial slide of the Astoria Boys and Girls Club.
And your second question was leaving out the line sets. If each room has PTAC, wouldn't all those units take more embodied carbon to build than fewer CUs and only evaporators for each room? You want to make sense of that a little bit more for Ed?
Well, unless Ed, if you understand the question.
Well, how are you, David? It's nice to see you.
Nice to see you.
I hope everything's well. The Boys and Girls Club project is UAI, and yes, this project is Think. Yeah, not to be obtuse, I might have missed it, so let's try. You're wondering if there's a potential for more embodied carbon with the PTAC system In
Well,
what way?
I guess I'm saying your analysis described the refrigerant lines, the line sets as a comparison. But I would guess my question was, what about the manufacturing of the equipment of apples to apples for the condensing units and the evaporators for a split system versus a package system?
Right. That's a great question. And it is one that we're seeing a lot of movement in embodied carbon space. Some of our state and city agencies are coming to that. There's more reporting and more criteria coming for the heavy construction materials, right? When you look at a building, most of the embodied carbon is in the concrete stuff, and then these other pieces are less significant, but of course very significant. We have not explicitly studied the embodied carbon in the manufacturing, right? What is embodied carbon? We got to build it, we have to transport it to site and all that type of thing. So no, I don't readily know if the PTAC or VRF equipment has more embodied carbon itself. The point was certainly we have more copper piping, which has an embodied carbon, and then the embodied carbon within the global warming potential of the refrigerant itself.
Understood. Thank you. That's very clear. I appreciate it.
Thank you.
Thanks, Ed. And thanks, David. Our next question up is from Scott Greenbaum. Scott, would you like to unmute? I know you had a couple questions. You want to start off with one or two?
Yeah, so question number one, we looked at for a large retrofit of a large luxury condominium rental place, putting the PTACs in. And the PTAC manufacturer came back and said, you can't run the heat pump part below the temperature of 32 degrees outside because we get condensate that drips down the side of the building, and we don't want to have icicles landing on the pedestrians walking below it. So can you explain how this has changed with the upgraded PTACs? I'll admit this is 2 years ago for NYSERDA application, because we were just going to leave the hot water coils in there to run below 30, which means we still have half the fossil fuels in the building, or well, probably 25%. And so are you putting internal drains to get that water away? Or, that's my first question.
Sure. Sure. That's a great question, and I appreciate it a lot. I'll start by saying there's a number of things for retrofit that are a little different than for new construction here, and I'm happy to talk about them in a minute if we want. But to the heart of your question, there's kind of a misnomer that just exists out there in a way that I want to kind of speak to first. A traditional PTAC, maybe just a hot water or a gas-fired PTAC, let's say, does not come with a condensate riser, right? It's cooling, and when you put wet water in contact with a coil, condensate forms. You have to deal with that somehow. So the way the traditional PTAC does that is with this really cool thing internally called a slinger. It grabs the condensate, and it literally is a spinning little thing, and it slaps it across the refrigerant piping, and it flashes, and it goes away. And there's an actual very, very small operating efficiency benefit that happens because you cool off the refrigerant circuit ever so slightly. The modern cold climate PTHPs do the same thing in cooling. So there is actually no condensate to dispose of. The concern that you're getting at, which is also very real, is actually defrost. The code hasn't even really addressed this yet because it's still called the condensate riser. What happens is with a heat pump, as it tries to heat at very low temperatures outside, the coil gets cold. It's right where heat pumps are moving heat. So it's bringing heat in, and it is rejecting, and it is making the coil outside. It's bringing heat in, and the coil outside is getting colder. So the coil freezes, especially when it's wet. Excuse me. It could be 20 degrees outside, but psychometrically, there could be a lot of water in that air. And so you can actually have frost buildup on the coil. And so the fear that you're getting at is that could theoretically turn into falling ice under the right conditions, and that's very real. So the modern cold climate PTAC or heat PTHP does something to protect itself. It runs in defrost mode. So like, let's say out of an hour, my office, the PTAC needs to be on for 40 minutes. There's 20 minutes it could be running to defrost what's developed on the coil and send it down a defrost riser, which is affectionately called a condensate riser. So yes, verse, it's a long-winded answer, but vice, a traditional PTAC, these have to come with a condensate riser, which is really a defrost riser. But if you install that, you can rough the defrost to, it's typically a PVC, 1-inch PVC riser. It could be 1.5 inches, depending on the size of your building. And you have to find some way to nest that within your envelope, or let's say, or you could leave it exposed. Usually you don't want to see a 1-inch PVC pipe in the corner of your room. So for retrofit, you would have to think out that detail, but it is certainly possible to manage, let's say.
All right, and so basically that's what I thought would be the solution would have to be something. You have to run in retrofit, you have to run a condensate, and then in new construction, obviously, it's easier. Whether we want to call it condensate or defrost, you're going to run a riser for the new construction somewhere in the interior of the building.
That's right. And I will say, depending, right, this is free, right? It's not condensate, it's actually serving the heating side, right? But so if you're abandoning, your building may have existing heating risers. There might be steam piping or hydronic piping. Where we've done this in retrofit, sometimes we will reuse that piping. So we find a way to rough to that pipe, and if we can qualify it for use, we're already done.
So, all right, well, I mean, I just wanted to see because the manufacturer wouldn't let us put it in because they don't want the liability. All right, and then my other question had to do with, so you're talking about blackwater. Well, let's say we're talking about an apartment building that has no third-party usages. Is part of your blackwater system coming off the shower drain systems and those systems, not toilet drains? You usually, if you're doing this, I've seen it in Singapore. They did it 40 years ago. They separated toilet drains from all the other drains. So that I can understand, but you still have the soap scum issue. And I know we were doing in the 90s, we were trying to preheat domestic hot water in apartment buildings. And after 2 years, we got zero heat transfer because of the insulating value of soap scum. And so maybe you can be more explain a little more about your idea. Are we just using clean water out of from refrigeration or stuff, or are we trying to recover heat also from the shower and sink drains?
Yeah, great. Also a great question. Definitely a big distinction between wastewater heat energy recovery. You wrap the shower drain pipe around incoming, and instead of 40, 45 degrees coming off the street, you pick up 10, 15, 20, 30 degrees, whatever it may be for your condition. No, this is not that. This is a product line that can actually handle solids without getting graphic, right? And you see the room, and they've done it before, and it's, everything's hermetically sealed and it smells fine. So this is quite literally using the sewer, and it is the core concept is relying on that temperature. We actually we tried barking up this tree in a different way some number of years ago, because we were trying to work also with DEP in the city to try and make a connection to a sewer. We wanted to use the actual sewer as a heat source sink. We didn't get that far, but the market has caught up, and now there are products that can actually handle this.
So how about the SOSCUN? Have you had any of these in place long enough to see if the SOSCUN does it?
Well,
Create an insulating issue.
yeah, I will admit we do not have a ton of operating data on that side, so it is a legitimate concern. And I myself will have to do, I have to do more digging myself, to be honest, just to understand exactly the longevity and how it deals with soap scum and the solids and that type of thing, and what the maintenance evolution looks like to make sure that the system continues to run at peak efficiency. So it's obviously a great concern and consideration, but the design intent is to basically handle it raw, so to speak.
Great answer. Great question. We're going to have to pause there just for a minute, but before we jump into events and have Kim take us through what's coming down the line, Ed, really amazing to hear your mindset and the way you share your mindset and see how you're always looking for these other opportunities for circularity. I love to know what you try to do with the drain water or or the freeze water that's coming through these internal pipes when we come back. Right back into the questions. I know the hour is nigh. So Ed, if you're able to hang out for a few more questions, we'd be thrilled to have you. And for those of you that have to get back to work, we understand. But for those who can stay, you're in for more. What do you think, Ed? Are you up for a couple more?
Always. Let's go.
Fantastic. Our next question is from Hernan, YE1. Hernan, are you with us still? Looks like you are. Looks like you're on mute. Would you like to unmute and ask your question, or I can ask it for you? Hernan asked, what kind of heat exchanger are you using to catch the blackwater temperature?
It's a good question. There's Piranha. Piranha is one of the leading manufacturers, is basically an off-the-shelf solution, right? So call it a turnkey kind of solution that comes with the tanking and the heat exchangers and the whole setup, so that it basically manages the stuff that we're talking about. You obviously need to size it to match your building load and that type of a thing. And you have to think a little bit, because it relies on the waste, right? So if the building's occupied, the building's occupied. If the building's not, it's not. But yes, thank you for sharing that. That's the link, exactly.
Well, I'm just repeating it. I am being the echo that I love to be. That was shared earlier. I can't remember who shared it. Our next question up is from, sorry, I've lost my way here for just a second. Lauren Bauman, who I believe had to hop off. And her question was, I'm not seeing information about operating cost deltas being considered in these decisions, which is critically important for affordable housing. Can you speak to that piece in the system's decision-making process?
Absolutely. It's a great question. My closing slide is a challenge, right? It is great to push and push, but we do need to stay grounded. And one of the ways that we do that is we challenge ourselves to think like others around us. I coach people internally even to say, right, how do we work better with each other? Well, we try to make our lives easier. I can make a developer's life easier, or a contractor's life easier, or a structural engineer's life easier if I can think like them. So all of these decisions are grounded in economic analysis, payback, outlay, net present value, and all that type of a thing. And we would not, sure, that a blackwater source heat pump, we'll pick on the blackwater source heat pump. For affordable housing, the developer is required to provide heat and hot water. And if the developer doesn't, then there's a utility allowance credit that comes, which is effectively a rent subsidy to the tenant so that they can afford to purchase their utility. So effectively, you have to pay for that use one way or the other. So if the COP on a blackwater source system is, we'll call it 4 versus an air source system, which is 2.5, what is the operating benefit? That is we want the developer to be able to claim that, because theoretically the blackwater system costs more than the air source system, let's just say, although that may or may not be true depending on the project. But there it is, right? What does it cost? What do I save? And utility costs for a non-affordable project in New York City? What are the carbon taxes, future carbon taxes that I mitigate? And rolling that all together again into payback period and net present value, so we can level these things and spend our dollars in the best possible way. 100% necessary.
Great feasibility study in a nutshell. Good answer. I love it. Are your feet moving down there below the Zoom screen? It looks like you might be good on your feet. So our next question is Jean DeJoannis. Jean, would you like to unmute and ask your question?
Well, I had a question about the blackwater heat exchanger too. How do you keep it clean? But we'll skip that. I'm wondering if you've done water-cooled condensers on when you have a large group of market walk-in coolers or any type of refrigeration equipment that needs cooling, and captured the heat out of that water loop to your domestic hot water.
Yes, that is one of the reasons why we love mixed use projects. We have another project that has effectively a 100,000 foot shopping mall on the bottom with 600 some odd apartments at top. And yeah, boom, I know, I love it. That's the scale we're at. And so that is exactly what I'm looking for. Like, if I'm looking for circular opportunities, that is exactly that, because there are it gets complicated, but there's a lot of different system options out there that can make simultaneous heating and cooling water, right? It goes back to the point of the graphic. One electricity use, you buy electricity once for two purposes. Right, if I can exchange the energy, right? So that COP can go from 3 to 6 in an opportunity like that. Yes, we have done that. And when I have the opportunity for that, then my feet are moving. I fall out of my chair. It's like it's the best day ever.
We did that in a college student center, which had a big commercial kitchen for the dining room and lots of coolers and needed lots of hot water. It's a beautiful marriage.
That is really awesome. I'll take circularity to one further step, really. One of the barriers to this type of thing is, I don't want to say entrenchment, but unintentionally, we have party lines, right? Here I have a project that has two distinct users. I have apartments and I have a market. They have distinctly separate uses. When we can co-develop like this building can, then I can consider these things jointly in design. The problem becomes, I have 100,000 feet of commercial space at the bottom of 600 apartments. What is it going to be? And you can guess, and believe me, we know that whole dance, like many of you probably do too. That retail is not what it is until it is. And even a lease signing isn't enough, because things change all the time. So this project and the Variety Boys and Girls Club that I spoke about at the beginning, I know what the commercial user is at the beginning, and I can directly tap into these circular concepts. Getting to them when I don't know what's going on in a mixed-use building is sometimes more challenging.
A problem we ran into was there was too much heat of in the refrigeration coolers for our domestic water needs at some times. So we needed to have an air cooler to reject it when that occurred.
Yeah, yep, that's exactly right. And that's also spot on, right? You're like second, third level of the concept here, which is unbelievable. It's like, right, what we just said for a blackwater source, it only works if the people are using the showers. And obviously we only need domestic water when the people are in the building. So that one is a little bit more straightforward. But if I have a market relying on apartments and vice versa, and the market goes out, we need to consider backup sources. And so that is also part of the feasibility analysis that needs to be carefully thought through.
Fantastic. Great question, Jean. Thank you so much. We're getting close to the final 15, and we've got 2 more questions from Enrique. Can you choose one so that we can fit Chris in too?
Sure.
Thanks.
I just wonder, how do you manage the ventilation with those P taps?
Great question. We're doing central ducted. We have not coupled with the PTAC that we're using on this project. We're working on other projects to try and use the more modern Italian style unit, the way that I called it, with the integral ERV. And there's different pros and cons and cost points and stuff there. But here we're just doing central ducted stuff to the roof.
Okay. Thank you.
Thank you.
Thanks, Enrique. And Chris Goodman, are you here with us still,
Yes,
Chris?
I'm here.
Hi.
Great presentation, Ed. Thank you so much. Just a question, maybe you already covered it. I was just curious from a developer standpoint how you kind of separate the heat pump system, the PTHP, for the heating season, and how they can bill for that, and, or they don't bill for that, they bill for the cooling, right? And somehow they have to cover the heating costs, but is it like separately metered? How does that work?
Yeah, that's also a really great question. Within the city, affordable housing is subsidized by HPD, the Housing Preservation Development arm, basically, of the building department. And they have struck a very clear policy on this, which has helped. It's a little weird, but I'll describe it like it to the uninitiated. It's a little bit of a head scratcher, but basically what we're doing is we're wiring the PTAC 2 ways with a rib relay, which is a rib relay is basically a fancy term for a flip-flop relay. So when you're in cooling, it goes to a developer panel to pay. When you're in cooling, it goes to a tenant panel to pay for cooling, and when you're in heating, it flips to the building panel. So there is a cost premium there. If you Google HPD's electrification policy, you'll get that pretty quickly. And it has changed subtly over time. And they're working on finding ways to kind of unlock more potential. And we're actually in a working group with them and some others that work in that type of space too. But that's the way we've been doing it for the time being, and how we're doing it here.
Great, thank you.
Thanks, Chris. And thank you, everyone, for joining us. Please connect with Ed Ettinger and thank him for this presentation. And go to passivehouseaccelerator.com and check out our latest podcasts, articles, videos, and come see us tomorrow for the component spotlight and sign up for March 7th's Reimagine Buildings. Ed, you have a great rest of your week. Thanks for joining us today.
Thank you all so very much. I can't tell you how much I appreciate this session.